the fundamental theorem of calculus part 2. If f is continuous on the closed interval ab, then for x which is greater or equals to a or less or equals to b, the definite integral between a and x f t dt is a function that is continuous on the closed interval ab, differentiable on the open interval ab, and d dx of this definite integral is f of x. This theorem says that if you have all the conditions, which means that f of t here is a continuous function on ab, and x is between a and b, including maybe a or b, then we can actually differentiate this definite integral. Look at the integral. The lower limit is the number, and the upper limit is x. And in this case, if we will differentiate this definite integral, we will get the following. This is just the function f of t, which is the integrand at which the t is replaced by x. Example. We are going to do this twice. First, we are going to do it directly. First, we are going to evaluate the definite integral of t cubed dt between 4 and x. A good antiderivative is t to the power of 4 over 4. And then we have to substitute the limits, x and 4, and take the difference. When we substitute x, we get x to the 4 over 4. When we substitute 4, we get 4 to the 4 over 4, which is just 64. Now, you can observe what happens when we are differentiating that. From the first part, we get x cubed, and from the second part, we get 0. Because when you substitute the number in the antiderivative, you get just another number, and the derivative of a number is 0. As you can see, this is the solution. Now we are going to apply the theorem. We can apply the theorem because t cubed is a polynomial and it's continuous everywhere. And here's the theorem. We have to write down the integrand, which is t cubed, and replace t by x, and we get again x cubed. Example. We want to differentiate the definite integral of this horrible function between 4 and x, which is at least 4. Because we cannot find the antiderivative of such functions, we are going to use the theorem. For that, first I have to show that this theorem is continuous between 4 and infinity. We observe that 5t is always continuous, but then we have square root. So t minus 4 plus e to the t has to be at least 0. But we know that because e to the t is always greater than 0, then t minus 4 plus e to the t is greater than 0 when t is greater or equals to 4. It means that this function is continuous on the interval 4 to infinity, including 4. So if x is at least 4, we can apply the theorem. So we're just going to write the integrand, which is highlighted here, and replace all the t's by x's. And we get that. Example. We are going now to do the same. We don't know how to find the antiderivative of sine t over t minus 1, so we have to use the theorem. We are just going to copy that, and instead of t, we are going to write x. But we have first to note that this is a continuous function for all values that are at least 2. The only problem with this function is when t equals 1. So if t is greater or equals to 2, then this function is continuous and we can go along and apply the theorem. And here's what we get. Again, this is just the integrand after switching all the t's to x. Pay attention. This is not true for x's which are greater or equals to 1, because the function sine t over t minus 1 is not continuous at 1. So you cannot include 1 on the interval of the integration, which means that if the lower limit here is 0, then the upper limit cannot be 1 or more than 1. Here are some combinations of the same theorem. Well, definitely I'm not going to do this directly, but maybe I can still use the theorem. The theorem is such that the lower limit of the integration is a number and the upper one is x. So I can just switch the limits of the integral. I would like to recall that you're allowed to switch the limits of the integration, but then you have to multiply everything by -1. If you observe at this integrand, this is a combination of functions which are continuous everywhere. So the integrand is continuous everywhere. Now I switched and I multiply by -1, so now I can apply the theorem after switching. Here's the integrand, and I'm going to just switch all the t's by x's, and don't forget the -1. And I get that. Now we are going to do a more complicated combination of the theorem. This is combination of the theorem with the chain rule, and we are going to do it using an example. If you look, the only problem here is that instead of a variable we have here a function, so we cannot directly go and apply the theorem. But I can make this 4x plus 1 a variable just by substitution. Please note that this function here in the integrand is continuous everywhere, so I don't want to bother now with that. Let's do then a u substitution. We will take u to be 4x plus 1, so the upper limit of the integral is going to be just one variable. But then we cannot have d dx. If the upper variable is going to be u, then we need to have d du. So let's figure out how to do it. If u is 4x plus 1, then du dx is 4. But d dx is d du times du dx. So we are now replacing 4x plus 1 by du, and we are replacing d dx by d du times du dx. But I don't care about this du dx. Now I got not only one variable as the upper limit, but I also got d du. So I'm going to take this du dx to the side right now. But now if you look at the bracket, I can go ahead and apply the theorem. It is just the integrand where all the t's are replaced now by the variable u. Now I'm going to replace all the u's by 4x plus 1, and the du dx is just 4. And I'm going to get that. Example. Let's now evaluate d dx of the definite integral between 0 and x to the power of 2 of t cubed plus e to the t dt, and then we will evaluate d dx of the same integrand, but now the limits of integration are x and x to the power of 2. And let's do it for all x which is less than 0. First of all, pay attention that x to the power of 2 is greater than 0 if x is less than 0. And I'm not bothered by this integrand, it's continuous everywhere. So let's now do what we did before. We're going to do u substitution. U is x to the power of 2 and du dx is 2x. So we are replacing d dx by d du times du dx, and also we have u instead of x to the power of 2. Now we are going to apply the theorem. Here's the integrand, so we are going to replace this by u. We know that this is continuous everywhere, and we can apply the theorem. And we get that. Now let's replace u by x to the power of 2. And we get this. Now we would like to evaluate this. I would like to recall that the integrand is continuous everywhere. And also, this is going to be very useful now. We know that we can split integrals like this. If c is between a and b, then the integral between a and b equals to the integral between a and c plus the integral between c and b. In this case, we know that x is less than 0. And we know that x to the power of 2 is more than 0. And that's why we can split this definite integral to two integrals. The first one is going to be between x and 0, and the second one between 0 and x to the power of 2. We also know now that the derivative of a sum is the sum of the derivatives. So in the first part, I'm switching the order of the limits, and don't forget to multiply by -1. And what I get is, from the first part, that it's negative of x cubed plus e to the x, because this is just direct substitution of x instead of the t in the integrand. And don't forget the minus. And for the second part, I'm using what I just did before. And I get that. If you noticed, I can also kind of give you a rule how to use this theorem in the case that the limits of the integral are between a number and a function of x. Let's call this function of x g of x. First of all, we take out the integrand, and now we're replacing t by g of x, and then we multiply by g prime of x. This is the derivative of gx. In general, we get that d dx of the integral between a number and gx of ft dt equals to f of g of x times g prime x, provided obviously that f of t is a continuous function on the proper interval. Example. Now let's do it directly. We know now that g of x is 2x plus 1 and g prime of x is 2. And we have no problem. This is a function that is continuous everywhere. So using that, I get, first of all, I replace all the t's by 2x plus 1, and then I multiply by g prime of x, which is 2 in this case.